Thank you, everybody, for coming. We're so excited to have you here at the ATARC Quantum Speaker Series. We are excited to have a wonderful speaker, but I wanted to let everybody know who hasn't attended before. Please, we hopefully will have time for question and answer. If you have questions, please mark them in the Q&A at the bottom or raise your hand and we will unmute you. Today's speaker, I'm Allison Schwartz, by the way. I am the Industry Quantum Working Group Chair from D-Wave, and I'm excited to invite my colleague, Andrew King, here to give a discussion. So he is the Director of Performance Research at D-Wave, which he joined us in 2013. He's received his PhD from McGill University and worked in graph theory and algorithms. And we're excited today to hear about some of the peer-reviewed research that he has been working on. And with that, Andrew, I'll turn it over to you.
Thank you very much, Allison. It's very nice to speak to you all today. I'm going to give a pretty high-level overview, at least from my perspective, and I would be very happy to get into more technical detail in the Q&A. And I have more detailed slides if anybody is interested. So I'm going to talk about moving towards quantum advantage, and that involves some research that we are doing right now and some research that we've done. And quantum advantage can be sometimes a bit of a slippery term because depending on who you ask and when you ask them, it could mean something different. So one type of quantum advantage we've already achieved, and that is a quantum scaling advantage in approximate optimization. And another type of quantum advantage, which is also known as quantum supremacy, is something that we're working on right now. Wherein we solve a problem that is impossible for classical computing resources to solve at an equal level of quality. So, without further ado, just an overview of quantum annealing research at D-Wave. D-Wave was the first company to offer a commercial quantum computing product, and we've been developing these prototypes for almost 20 years. The company has existed for over 20 years. And we are developing gate model processors as well, but I'm going to focus on quantum annealing, and all of the products that we've had so far commercially available have been quantum annealers. So this, when I started in 2013, the new product was D-Wave 2 with 512 qubits. And now we're at Advantage, which has 10 times as many qubits, over 5,000. And that's the primary apparatus that I'm going to use for the experiments that I'm going to describe. So quantum annealing has been applied to a variety of different industrial verticals, and we've had some success from large firms and small startups as well, with the Creative Destruction Lab at the University of Toronto incubating some of these. And these areas include drug discovery, scheduling, manufacturing, and materials science. So some of what I'm going to talk about today is more on the materials science side. So I'm going to assume a fairly general high-level audience, and so I'll spend a little bit of time explaining what quantum annealing is. So quantum annealing is an optimization heuristic that exploits quantum fluctuations to drive dynamics. So that means that you are using quantum effects to help you find good solutions to an optimization problem. Now, quantum annealing is kind of naturally described as a contrast to simulated annealing or thermal annealing, which is a technology that has existed for thousands of years, kind of tempering a metal into a very stable state is thermal annealing. And simulated annealing is a meta-heuristic that was invented about 45 years ago and is incredibly broadly applicable, very flexible, very useful. And it involves basically setting up your problem as an energy potential. So you just kind of set up a physical system of spin so that the low energy solution is a low cost solution for what you want to do. And it doesn't matter what you want to do. This is just how it works. And then you kind of have this particle, which is your current solution, bouncing around at a high temperature, and then you gradually lower the temperature. And as you lower the temperature, the particle settles into a low-cost solution or a high-quality solution to whatever it is you want to solve. And the way that we can encode this energy landscape is with a classical Ising Hamiltonian. So for those of you who are not physicists, a Hamiltonian is just an energy function or a cost function. So I come from a computer science background, so I've had to learn the second language of physics. So this is just a cost function, not a Hamiltonian. And this is all classical. And so normally in simulated annealing, we think about having a constant energy landscape and then gradually lowering the temperature. But we're going to do it slightly differently because this is how it works in our hardware. So instead of lowering the temperature, we're going to keep the temperature constant, and we're going to increase the strength of the energy, the energy landscape. And so this is equivalent because you just divide one by the other basically. And we don't modulate the temperature in our processor. So if we want to update this with some 21st century flavor, we're going to add quantum fluctuations. And so just like temperature, quantum fluctuations help your current solution move around and explore the landscape. And you can find certain situations in which this is provably helpful. And I'll discuss that in a little bit. So we start with very high quantum fluctuations and attenuate the quantum fluctuations so that in the beginning, the system is dominated by quantum fluctuations and it's in a superposition state. It's fully quantum, but also fully boring. It's trivial. It's a very easy problem to solve. And then if we do this right, if we gradually lower the quantum fluctuations, we end up in a low-cost solution of an intractable optimization problem. You can encode NP hard problems within this framework. Okay, so we're also going to throw away the temperature. And this is something new that we can do by annealing very fast so that we remain within the coherent regime of our qubits. And also by extending the coherence of our qubits, we make it so that we don't have to anneal so fast. But in any case, we can ignore the thermal environment and we only have quantum fluctuations now. And this makes things a lot easier to analyze theoretically. So simulated annealing, thermal annealing is really good. It's really effective and people use it for all sorts of things. So why should we expect quantum annealing to be any faster? One of the disadvantages of quantum annealing is that we don't have this really rich, solid theoretical framework that gate model quantum computing has. But once we throw out the thermal environment, things get a lot easier, and we can explain why it should be faster than thermal annealing. So one reason is coming from condensed matter, and not just condensed matter theory, condensed matter experiment. So about 25 years ago, there were a series of experiments by Brooke et al. And other permutations of authors in magnetism labs, where they would take a magnetic spin glass, and a spin glass is just a physical manifestation of a hard optimization problem. Basically, it's like if you ask the physicist to build a statue of a hard optimization problem, it would be a spin glass. And so the spin glass phase diagram has not just one way to get from the easy region to the hard region. We want to be here. There's a manifold of paths that we could take. And so thermal annealing is going to go through a thermal phase transition. Quantum annealing is going to go through a quantum phase transition. And they actually compared these physically in a lab by finding a magnetic alloy that they could treat as a quantum annealing experiment. And what they showed was evidence, indirect evidence, consistent with the hypothesis that quantum annealing would solve this problem faster than thermal annealing. And so we have everybody who does anything with cutting edge technology, whether it's in a magnetism lab or in a quantum computer, they always have limitations and they always have strengths and weaknesses. And one of our strengths is that we can take this experiment, put it in a programmable quantum system, and we can get direct evidence of quantum speed up here instead of indirect evidence in a non-programmable sample. So the big result that we published last year is that, well, actually just a few months ago, we submitted the paper last year. The big result that we published this year is that we can reproduce this quantum experiment in a programmable system and show direct evidence of a quantum speedup. The other reason that we think that quantum annealing should be fast came out around the same time, so 98 from Kadawaki and Nishimori, and they studied very small instances where they can brute force the Schrodinger dynamics. So they can actually, the quantum dynamics of these systems are totally intractable. The memory requirements blow up exponentially, and it's extremely hard computationally to see what these quantum systems are going to do, unless you do a really tiny system, like 8 spins. And then they showed evidence that you could optimize these systems in certain cases faster than simulated annealing. So these are two parallel support columns, basically, for why we would expect quantum annealing to work. Now, I'm going to talk about two basic classes of applications. One is simulation and one is optimization. So optimization is usually what somebody wants to do if they don't care about quantum physics. So that includes a lot of customers and people who are curious about quantum annealing. And so if you want to optimize, is to read out the system or sample the system after the quantum fluctuations are totally gone. So this is at the end of the anneal. So you start here, you go here, and then bang, you look at your state here, and you see how good the solutions are. But if you want to simulate a quantum system, you want to actually interrogate the system when there's a mixture of quantum fluctuations and classical interactions. So you might want to do it here. And so we're actually going to do this kind of in an in-between way, as well as looking at optimization. So one way to look at it in the middle is to go through the middle really fast in a system where you have something called a critical slowing down. So basically the dynamics slow down precipitously at this point. So they're effectively frozen, and you can look at what the system was at this point, even though you're reading it out here. Maybe I'm getting into a bit too much detail, but these are two classes of applications. So there's a group of scientists who asked the question, can we detect a quantum speedup in quantum annealing? And they asked this question about 10 years ago, and the answer was no. And it wasn't because of anything that they did wrong in their science. It's because of the regime in which they were looking. So there were a couple of issues with the regime that they were looking at. One is that they were looking at very slow anneals. And so for very slow anneals, you kind of get thermal fluctuations impinging. And so you get a funny mixture of quantum and thermal that's quite hard to analyze. And the other issue is that they were looking at exact solution of spin glass problems. And so for analog computers, including quantum annealers, exact solutions are maybe not the wheelhouse. And this is something that we're not actually worried about, because even finding approximate solutions to spin glass problems is intractable, classically intractable. So we're perfectly comfortable saying that we want approximate solutions to the optimization problem, because doing this with either any known quantum algorithm or any known classical algorithm, it's going to take exponential time. It's just that the quantum exponential is much faster than the classical exponential. So what we showed in our publication this year is that we do find a scaling advantage. And we see the scaling advantage in the form of a faster decline of residual energy density. So residual energy density is a physicist's way of saying how much money is left on the table when I'm finished doing the best that I can with this optimization problem. And so what we're looking at here is we are annealing slower and slower. And we're saying, okay, if I spend twice as much time working on this optimization problem, how much better does the solution get? And so you get more payoff here, that you have a steeper slope, you get a greater payoff for spending more time doing quantum annealing than simulated annealing or simulated quantum annealing. So I'll get into a bit more detail, but not much. And this is the programmable analog of the Brook et al. Experiment in the magnetism lab from the 90s. So this quantum optimization of 3D spin glasses was a collaboration with Anders Sandvik at Boston University. But first, we did a 1D coherent annealing experiment. So basically, we're doing a very, very, very easy optimization problem that is extremely well understood. And not only that, probably hundreds of papers have been published on this very basic system. And also, you can solve the quantum problem exactly just by exploiting the structure. So this is nice because you know exactly what the answer should be. And so you can compare it to the output from the quantum annealer and figure out whether or not everything makes sense. And without getting into detail, everything does make sense. So if you look at the single qubit measurements, we measure the parameters of single qubits. We get an equation for the coherent theory of the residual energy density that we expect. And what we get from a measurement of 2000 qubits is very close. So it's just a few percent off, which is very good in this setting. Maybe more importantly, or equally importantly, if you go quite fast in your anneal time, so this is nanoseconds, we're talking about 30, 40 nanoseconds. In this regime, it doesn't matter what the temperature of the system is. And that suggests that this is a coherent computation where you're not interacting with the thermal environment. And so you can throw out all this complicated thermal stuff and just look at the quantum system in terms of the dynamics and what you expect to happen and what you observe. So briefly, this paper, which was in Nature Physics last year, shows that we can do, we can get exactly what we would predict basically in a very well understood and simple to calculate system with no fitting parameters. Okay, so this tells us that we have our feet on the ground and we know what we're doing. Now we want to do something that's much less understood. So we look at 3D spin glasses, and this is the statue of the hard optimization that the physicist has built. So like I said with this Kadawaki and Nishimori paper, we can brute force the dynamics of small systems. So that's the first thing that we did. And we make a graph like this, and we make random interactions. And this is how we build our interesting energy landscape. And then we brute force the Schrodinger dynamics. So we know exactly what should be happening during this quantum quench, as it's called. And we find, just like we did with the 1D experiment, we find very good quantitative agreement. And then we move on to larger systems. So we grow the system like a 3D spin glass problem up to 2,700 logical spins. So we're talking 5,400 qubits. This is much larger than any other quantum simulation ever performed, programmable quantum simulation. And we program random optimization problems into this lattice structure. And then we look at the kind of the coarse scaling, the finite size scaling of these problems, and we find that these are consistent with the universal critical exponents that have been extracted in previous studies. Okay, so like I said, I'm not going to get into a lot of detail, but we have this slope of the energy reduction, and it is steeper than the classical algorithms. So that's just one piece of evidence. In terms of how long this actually takes, you can see that the annealing time on the x-axis is in nanoseconds for quantum annealing, but it's in Monte Carlo sweeps for the other two methods. So if we put it in nanoseconds on a CPU, these two methods are way out here. So they're kind of hundreds of thousands of times slower. And these are, in this case, these are theory lines. So these are theory lines coming from the known critical exponents. And you see a little bit of deviation. And this is because, this is really technical. This is because we're interrogating the system at way after the critical point instead of at the critical point. So you get a bit of a deviation. And then this is the boundary of the coherent regime, which we want to expand using improvements to materials and fabrication. So this is the quantum advantage that we have achieved, and the quantum advantage that we want to achieve is going to be in simulating a quantum quench. So like other quantum supremacy efforts, what you want to do is you want to set up a quantum dynamical system, and you want to generate the output of passing through this system. And you want to generate it to high fidelity, and you want to present evidence that you are not only doing something hard, but you're doing it correctly. And so we've been making the first building blocks of this, and the leading competition for classical methods is matrix product state, so tensor networks, DMRG, PEPs, methods like that, and then neural quantum states is the other basically track of research that we need to compete against. These two methods can faithfully reproduce the quantum dynamics of such a system at great expense. Okay, so we need to do this approximately, and we need to do it to high fidelity as well, so that we know that we have the right answer. And one thing that I haven't shown is another one, which is Monte Carlo methods. So you also want to make sure that there's no fast classical method that can spoof the output of the quantum system more accurately than your quantum computer. Because of course, these are noisy quantum computers and they're analog, so there are going to be errors. You just want to make sure that these errors are smaller than any errors that you can get with any efficient algorithm. So far, we're looking at a few different topologies and sort of lattice geometries, and it looks like classical is going to have a very hard time competing with this. So this is a 5,000 qubit simulation. It's really difficult to come up with anything classical that can handle this. So just to wrap up, we've made programmable Schrodinger dynamics on over 5,000 qubits. And this is, we not only get a classical optimization scaling advantage, but we also get a system of quantum simulation that is, as far as we know, totally intractable beyond a couple of hundred qubits. So this was published in Nature a few months ago, and there's an archive preprint as well here at this link. And also we want to show that this computation can be the core of something that is bigger than just the QPU. So you can hybridize this method. And we have shown a way of hybridizing this 3D spin glass optimization method for larger than lattice or larger than chip problems. And this was published, I think earlier this year, maybe January, in ACM Transactions on Quantum Computing. And so that's what we're working on and what we've achieved recently. And I'd be happy to take any questions. Thank you.
Thanks, Andrew, so much for that. That was very thorough and exciting research that you've done. As we mentioned, please, if you have questions for Andrew, put them in the Q&A, the chat, or raise your hands. I did have a question that actually came to me on the side. And the thought was, the question was about 3D spin glass problems. And, what do those kind of look like in real world terms for folks that are not the scientists here, but are trying to solve public sector needs or what have you? Is there a way to kind of describe 3D spin glass types of problems? There's always a balance of how technical you should be. So it looks like a 3-dimensional cubic lattice of variables, but it doesn't matter what it looks like. What matters is how it behaves when you change the parameters of the problem. And so if you ask a computer scientist to build a statue of a hard optimization problem, this will be a max satisfiability problem. And so they'll make some random set of clauses and say, satisfy as many clauses as you can at the same time. And both of these frameworks have very clear phase transitions in hardness, so you can tune the hardness of them. And there are no known efficient algorithms for this regime. So if you do it in 2 dimensions, there are actually combinatorial algorithms that you can use to exploit the geometry and get to exact solutions in polynomial time. It's not the case in 3D. So basically, we want to do something that is simple but also very hard, and that's how we get to 3D. Wonderful. We have a question in the Q&A. The presentation makes sense on how quantum annealing will provide an improvement over thermal annealing. How do we know that quantum annealing would provide a performance improvement over state-of-the-art optimization techniques, non-annealing or operations research?
Well, that's always a very important question. So depending on the application, you I mean, you might have like branch and bound, cutting plane approaches, or mixed integer approaches. What we're focusing on right now in terms of performance research is stuff that is closer to the native language of the processor. And so that is naturally more work to get to certain applications. So this is very close to some applications, but some of them are not really going to be a natural fit, and we're never going to be able to solve all optimization problems. It's nice that we can say that it's NP complete, but in terms of people actually solving problems in industry, that's not good enough, because if you say, oh, there's a polynomial method for translating one into another, that might not be good enough. Polynomial is often not fast enough. So I would say that depending on your application, either quantum annealing is not a panacea for all problems, but it is going to be very effective for some problems. And then there's going to be a range of everything in between. And for some of them, depending on how far away it is, you're just going to have to benchmark it against more algorithms. Because for a lot of problems, simulated annealing is a very, very effective method. And depending on how hard you want to work on it, or how fast you need a solution, you might want to move to something like parallel tempering or other multi-canonical methods. But maybe I'll just leave it at that. It depends, in 2 words.
Wonderful. We have 2 questions that came in the Q&A. I'm going to take the second one first. Andrew, D-Wave platform, it appears, is restricted to Ising type Hamiltonians. Is that an inherent limitation of the way D-Wave qubits are configured? They're just curious.
Yeah. So Ising and Cubo, so it could be Ising, or it could be Ising is ±1, Cubo is 0, 1, more natural for certain application types. But the Ising is closer to the physical description of what we're actually doing, but you can translate between the two very easily. So if you want to solve a Cubo, this is something that very easily and naturally translates into an Ising model. But as soon as you want to introduce non-binary variables or constraints, you have to move to hybrid methods and indirect ways of expressing those in terms of binary variables, just like you do on a classical computer.
I think that leads great to the next question, which is about D-Wave customers and looking at the types of problems they're solving. How do those relate to the spin glass problems in your research? Does it stack up to classical optimization approaches? And do we have a cost or time savings?
That's a very complicated set of questions. So most of the industry applications are done with the various versions of the D-Wave hybrid solvers. And this is, so in terms of what I can talk about, most of this is trade secrets. So this is actually why we wrote this paper on hybridizing the 3D spin glass approach, because this is something where we could show it off and we could describe exactly what we're doing. But some of them, so let me just back up a little bit and say that nobody in any quantum platform has done anything in an application that cannot be done with a classical computer. And if they did, you would have heard about it. So they are solving very hard problems with the hybrid solvers and with a time advantage. And there's also, companies coming to D-Wave for solutions and finding higher quality of output than anything that they've seen before. But that's different from saying that if you put all this work into it and only use classical hardware, you're not going to also get an improvement over the state of the art. So I would say that's where we are right now. So people are solving hard problems with quantum and they're getting great solutions, but that's not the same as saying that you can't get great solutions in other ways as well.
Well, thank you so much for your thoughts and your time. We're at time now, so thank you everybody for coming. We hope to see you at a future quantum speaker series, and we appreciate your time. Thanks, Andrew.
Thank you.